problem 3 from last year exam paper. And today what I want to do, so we will just look at a problem which is very similar to a problem from homework. It is an exercise from lecture notes 3. I will show you now. It's almost identical. So we have exercises. Let's add this one. So this is what I want to look at now. So there is a two-dimensional map. Did you start recording? Two-dimensional map. X n plus 1 is xn squared minus yn squared plus parameter p, and yn plus 1 equals to 3xn. So we have two-dimensional map. And there are two problems stated. Same problems will be for first, I think it's first problem in homework 4. So consider the cycle of radius r centered at the origin. Show that this cycle is mapped under one step into an ellipse. And sketch the ellipse for a equal to 1 and r equals to 1. So first what we want to do, we want to show that circle transfers into ellipse. What means circle? Circle means circle of radius r. X naught is r cosine phi, and y naught is r. So this way, if we r is fixed, but if we change phi, phi will be parameter. Let's say between 0 and 2 pi. So if phi changes between 0 and 2 pi, it will be points on the circle, right? And so we started with this point of the circle, and what we will get? So the question is, x naught, y naught is given, x1, y1, we want to find. X1, we can find it using this formula. It will be x naught squared minus y naught squared plus b. X naught is r cosine phi, it's r squared cosine squared phi minus r squared sine squared phi plus b. So what I can put, I can take r squared outside, so it will be cosine squared phi minus sine squared phi plus b. What is this? What? Cosine squared minus sine squared. Who remembers these trigonometric identities? What it should be? Cosine of 2 phi. Alright? Do you remember this? Yeah? Good. So what we got is x1 equals to r squared cosine 2 phi plus b. We found x1. Let's find y1. y1 is 3 x naught y naught See, x naught is our cosine phi, y naught is our sine phi. So what we got is 3r squared cosine phi times sine phi. What is this? Half of sine of double angle. So it will be, I will try to see over r squared, and here will be sine of 2 phi. So what we got? x1 is function of cosine 2 phi, and y1 is function of sine 2 phi. It already indicates that we can construct circle or ellipse out of these two. Can you see it? So what we want to do, let's put it like this. We want to show the code part. We want to bring it to this point. Which is another trigonometric identity. Yeah. Now cosine squared 2 phi is x1 minus e let's say over r squared. Yeah, this was for all places. Is it okay? Can you see? Yeah. And sine squared of phi, we can extract it from here. This will be equal to 2 over 3 by 1. 1 over r squared. Y1 over r squared. Now this is correct. This is already, you can see that this is equation of ellipse. Yeah? x1 minus e squared plus 4 over 9y squared equals to r to the power. This is ellipse. Okay, so this is what we prove. Now what we can do, we can try to plot it. So how to plot it? Let's say this is x1. So center of ellipse at point A0. So this is A. So here, let's say this is center of ellipse. Now, if y equals to 0, it will be, so it is r squared here. And r squared. I will put it like this, it doesn't matter what you do. So this distance is r squared. And this distance is also r squared. Does it make sense? Yeah? Because if y1 is 0, then x1 minus a squared will be r to the power 4. Therefore, x1 minus a equals to r squared. So here it will be plus r squared and minus r squared. Now we can put it different way. Now we say if x1 equals to a, then y will be equal, y y1 squared is 9 over 4 r squared, y1 is r 3 over 2 r squared. This is 3 over 2 r squared, and this is minus 3 over 2 r squared. So therefore it will be extended this way. Yeah, so it's stretched, 50% stretch vertically. Does it make sense? Did you get it? So what we need to find out what is vertical scaling, horizontal scaling and vertical scaling. For horizontal scaling we put y1 equal to 0 and find that x1 minus a should be equal to plus minus r squared. This is what we found here. x1 minus a plus minus r squared. And another, for vertical scaling we say, okay, x1 equals to a, this disappears, and now this should be equal to this, which means that y1 equals to plus minus 3 over 2 r squared. 3 over 4 r squared, 3 over 2 r squared, r squared. So this is like 1.5 times longer than this distance was stretched vertically. This is, well, it is like problems, pretty much mass 101 problem, maybe even school problem to sketch ellipse. So we, if a equals to 1, this will be 1. And if r is 1, then this distance is also 1. So this point will be a plus 1, and this point will be a minus 1. This point will be 3 over 2, and this point will be minus 3 over 2. If r equals to 1 and a equals to 1. Yeah? But it is all the same. Good. This is not quite related to what we're supposed to do in our model, but for it's quite interesting general problem, general mass problem to practice. What is more related to our material is problem B. It's problem B, we should find fixed points and analyze their stability and to deduce on bifurcations which take place in this system when parameter A is changing. Have a look for fixed points. Fixed points are roots of algebraic system. Algebraic system is x equals to x squared minus y squared plus 3 and y equals to 3x. So all roots of this system, of this algebraic system, are our fixed points. Yeah? So from this, we conclude from this, we say that A is a y is 0, that's one solution, and second is x equals to what? X equals to A is a y is 0, or x is 1 over 3. Yeah? If y is 0, this second equation satisfied, 0 equals to 0. If y is non-zero, then we can cancel it. It will be 1 equals to 3x, which means that x is 1 equals to 3. So second equation has two roots. Now to satisfy first equation, y so we put here y equal to 0, and we get x equals to x squared plus a. Which means that x squared minus x plus a equals 0. And from here we can use that x 2 equals to 1 plus minus square root of 1 minus 4a over 2. So what we found? We found that we have here two fixed points. For two fixed points y equals to 0, and there are two variations of x over 0, and these two fixed points exist if one is more than 4a or a is less than quarter. If a less than quarter, then we have these two fixed points. Make sense? Yeah? And if x is 1 over 3, then we put x equal to 1 over 3. Here we get 1 over 3 equals to 1 over 9 minus x plus a. And from here we get y squared equals to a minus 1 over 3 plus 1 over 9. It's minus 2 over 9. Am I right? Therefore, y12 equals to plus minus square root of 8 minus 2 over 9. So what we found? We found, at the end, we found four fixed points. First one, y equals to 0, x equals to, say, 1 minus square root of 1 minus 40 over 2. Second one, y equals to 0, and x, I put here 1 plus square root of 1 minus 40 over 2. Third fixed point is x equals to 1 over 3, and y3 equals to minus square root of a minus 2 over 9. And fourth, x4 equals to 1 over 3, and y4 equals to square root of a minus 2 over 9. Good. Now what we know that these two exist if a is less than quarter, and these two exist if so a should be more than 2 over 9. Yeah? A more than 2. What are bifurcation points here? So one bifurcation is this, a equals to quarter. So I can put here. So when a equals to quarter, this cancels with this. And at a equals to quarter and a equals to 2 over 9, we will have what kind of bifurcation? Who remembers? Which details? How it's called? Anyone? It's called fold bifurcation. I have spoken about this last Friday, but since this is important story, I will mention it again. So I can even put it like this. So bifurcation diagram. Parameter E, and also y equals to 0, I will ignore it, I will put here x. So first two. When E equals to quarter, this they merge and equal to half. So first fixed point is at the same position as second, and it's half. If E is more than quarter, we don't have them. If E is less than quarter, we have them. So this will be something. I don't know which one is stable, which one is not, but let's say this is minus. This is x1, y1, and this is x2, y2. Yeah? So y is always y is 0 for both of them, therefore it's not so important, but x is changing. X is so they will coincide when E equals to quarter, but if E is more than quarter, they don't exist. If E is less than quarter, so they both exist. One of them, it's property of falsification. One of them should be stable, another unstable. I just don't remember who will be. So we should check who is stable, who is not. Or put in, maybe they both are stable. So one of them subtle, another is not. So in 2D it's something like this. Also, I have spoken about this last Friday. Who remembers this? Who was last Friday? There were not many students. You've been there, yeah? You remember this story? Okay. And here it is same kind of story. So this is another bifurcation diagram. Now x is constant. E, y. So this is 2 over 9. If E is less than 2, so when E equals to 2 over 9, y 1 equals to y2 equals to 0. So this will be something like this. So this like this. I can put it like this. This is x3 y3, and this is x4 y. If E is less than quarter, we have 2. We have 2 fixed points. What happens if E is more than 2 over 9? How many fixed points we have? Question. I will put it like this. Quarter is under here. Am I right? Correct? Quarter is more than 2 over 9. Quarter equals to 2 over 8, and 2 over 8 is larger than 2 over 9. Therefore, in this place between 2 over 9 and quarter, we will have 4 fixed points. They all exist. Make sense? Good. And well, it says, okay, so what you see is this, it simplified, since it takes quite a lot to analyze everything. This problem says just look at, well, let's say, consider all of them. So if E is more than 2 over 9, then all 4 can exist. Therefore, we should analyze all 4 for stability. Yeah? Okay, let's try to find out is stable, who is not. So 2 to analyze the stability, what we should do, what is procedure to find out what kind of fixed points we have, possible fixed points, to analyze the stability. What we do, we
look at the derivative.
yeah, Jacobian it's called. We create matrix which is called Jacobian. Here should be derivative of, so this is x line, this is g of x line. And here the derivative f over x, derivative of y, derivative of g over x, derivative of g over y. And this is derivative of this over x is 2x, derivative over y minus 2y, derivative of g over x 3y, and here is 3x. So this is our Jacobian. And now we will need to check, to find Jacobian at all of these fixed points and to find out eigenvalues for this Jacobian. Yeah? Let's start with this first one. So Jacobian at x1, y1 equals to, so y is 0, 2x and 3x. Okay, this will be 2x1, 0, 0, 3x1. Eigenvalues 2x1 minus lambda, 0, 0, 3x1 minus lambda equals to 0, and from here we find that lambda 1 equals to 2x1 and lambda 2 equals to 3x1. So this is lambda 1 minus square root of 1 minus 4a, and this will be 3 over 2, 1 plus square root of 1 minus 4a. So when a equals to 2 over 9, 2 over 9 on one side. So h here should be, yeah, it says 2 over, yeah, so when a equals to 2 over 9, am I right? Well, probably we can put that. 2 over 9, okay. It's 2 over 9. 8 over 9 here. 1 over 9. So lambda 1 will be equal to what? Lambda 1, when a equals to 2 over 9, equals to what? 1 minus 1 third, 2 thirds, yeah? Am I right? Is it correct? Yeah? 2 over 3. Okay, and lambda 2 is 1 plus third, it's 4 over 3, it's 4 over 2 is 2. So what is x1, y1 is sub. 1 lambda is less than 1, and another lambda is more than 1. Who remembers what is subtle, what is not, what is spiral or focus? You remember this? So this was, well, it's very important. It was in one of video lectures, and you supposed to know. I even talked about this, I think last Monday. If both lambdas between -1 and 1 we have stable, not if they are real. If both lambdas more outside of -1 and 1, it is unstable not. If one of them between -1 and 1 and the next one is outside of -1 and 1, then it's called subtle. So this is case. So this is subtle. It is unstable. Anyway, now what we can add. So this was about this guy. Now what is about this guy? y2x2. Now let's check second one. Eventually it will be, all should be the same. So Jacobian is still the same because y is 0. Therefore this should be equal to 0. It is fine. But now x here should put here x2, and therefore lambda 1 equals to 2 times x2, which is 2 times, which is 1 plus this square, 1 minus 4a over 1 plus square root of 1 minus 4a over 2. 1 plus square root of 1 minus 4a, and lambda 2 would be 3 over 2 is 2, which is 3 over 2, 1 plus square root of 1 minus 4a. Now, what is this? By the way, in previous one I made a mistake. If it was x1 here and x1 here, so this was minus, and minus, I think, for some reason I put here plus. So previous one it was, this guy was 1 minus 1 over 3, which was 2 over 3. Fine. 1 minus 1 over 3, 2 over 3, and this equals to 1. Right? 3 over 2, 1 minus 1 over 3, 1 minus 2 over 3, 3 over 2, so lambda 2 equals to 1. For this guy, lambda 2 equals to 1. So this order is, okay, let's keep it like this. Plus. Lambda 1 equals to what? It is 4 over 3. Yeah? This is 4 over 3. Am I right? Can you check it? So A is 2 over 9. This is 2 over 9. This will be 8 over 9. 9 over 9 minus 8 over 9. 1 over 9. Root is 1 over 3. 1 plus 1 over 3, 4 over 3. And this will be, so this is more than 1. Here will be 4 over 3. This will be 2. So this is unstable node. So these two guys we found. Now we should analyze these two guys. So these two guys appear when E equals to 1 over 9. 2 over 9. And what we need. So Jacobian at x3 y3, x is 1 over 3. So it was 2x minus 2y, 3y, 3x. This will be equal to x3 is 1 over 3, it's 2 over 3. Here will be 1. Y is minus 2 minus 2 times minus 2 over 9. And here will be 3 times minus 3 times square root of A minus 2 over 9. So we're supposed to find here eigenvalues. And is it if E equals to if E equals to 2 over 9, this will be 0, this will be 0, 2 over 3 and 1. And this will be same for both of them. And it was a 0, 2 over 9, and then quarter. Maybe we should look at quarter. Find out how stable is that. If A is quarter, let's say, then this will be 2 over 3 minus 2 times over 8 minus 2 over 9. 9 minus 8, 1. 1. This is something. I don't want to go into this because probably there should be some simplification. When A is less than 2 over 9, then they all exist. question is, who is who? So here we found this guy is saddle, it's unstable. Here also one of them should be saddle, one of them is not. Saddle will be unstable, not most likely will be stable node. The question is, who is here? Not who is saddle. We can find the eigenvalues, but this looks to be quite heavy. Maybe there is something easier. Y equals to C. By the way, if E is 2/9, can we check who was these two guys? I think we can find out like this. So we may have here y equals to 2/9. If A equals to 2/9, this is subtle, this is unstable node, it's fine. But this guy, let's check this guy. Here y1 equals to 0 and x1 equals to what? X1 equals to what? So we check it. 1 minus 4 times 2/9 divided by 2. It is 8/9. Yeah, 8/9. This will be 1/9 minus 1/3. This will be 1 minus 1/3 divided by 2 plus 1/3. Now I see what is it. So you see, when A equals to 2/9, this guy is 0, 1/3. And this equals to these two guys. X is 1/3 and y is 0. X. Now what happens? So this is what this guy was subtle. And this is subtle. And this was not unstable. So here we have 2/9. It gets y equals to 0 here, and x equals to 1/3. X equals to 1/3. Somewhere here, this root coincides with these two. So we have 3 roots coinciding in one place. What kind of bifurcation should be there? So when 3 coincide, it will be pitchfork bifurcation. You should watch it again. So when A equals to 2/9, it will be pitchfork bifurcation. Then this guy, this saddle, should become should become stable. You remember what we got here. One lambda was less than 1 and another was equal to 1. So when it's equal to 1, it came to the point where there's a bifurcation. Bifurcation always associated with lambda equal to 1 or minus 1. And this bifurcation was this place where these two guys appear. And this is its signature of pitchfork bifurcation. One root pre-existing, one fixed root pre-existing, that's this guy, and two more appear. If this is changing its stability from so these two, it is like this. So this becomes stable and this becomes unstable. I think it's this. No, it is stable. So since it was unstable here, these two guys will be stable, and this gets stable. Probably, what I want to say, you can go into eigenvalues. It will be long computations, but eventually you should come to the same conclusion. Here, at this particular problem, so the main idea here is to understand that this guy will coincide with these guys when they arrive. And therefore, it should be pitchfork bifurcation. So this is the main point. And when you found that it is pitchfork bifurcation, next point is to, instead, so we have this, x1 by 1, we have this, x3 by 3, and this, x4 by 4. So they merge here. This guy, which is x2 by 2, has nothing to do. It lives its own life. But these three guys merge here, and when they merge, stability of x1 by 1 should change. So it was settled here and become stable node here. Should become. And these two, if they appear, they should be stable. Therefore, this should be two stable nodes, I think. So it should be this kind of scenario. But you can check it by looking at eigenvalues. So I didn't go to eigenvalues because it looked to me quite heavy. So I can easily make mistake on the blackboard, on the whiteboard. But you can take your time and check it at home. Okay, so this is interesting problem anyway. And this, as I said, it's very, I think what you got, for your homework, it's a bit easier. So here was 2, and therefore what happens, so there is no this overcut. So this, you have 2 fold bifurcations which take place when A equals to quarter, but then shift already, and there is no any other complications. So for your homework, it is easy. Okay? And most of this, there is problem number 3 is a bit interesting. We can discuss it on Friday. But problems number 1 and 4, this is problem number 1, like problem number 4 is pretty much same style. Problem number 4 is, in fact, in one of my videos. I talk about Helland's map, and it is exactly problem number 4, almost exactly. Yeah. Okay.